Swayam Prabha. Digital India. Educated India.
Namaskar, welcome to the 5th week of our course on basic electrical circuits. So, in this week basically we will talk about the first order and second order circuits, and particularly today we will talk about the first order RC circuit. So, let us see what do you mean by first order RC circuit. So, before going into the RC circuit particularly, let us understand what is the meaning of first order circuit. So, what we will do in the first order circuit, we will discuss about two types of simple circuits which are comprising of resistor and capacitor, and a circuit which is comprising of a resistor and inductor. So, these are typically called as RC and RL circuits. Now, the analysis of these RC and RL circuits is done by applying the Kirchhoff's law as we did for the resistive circuit. Now, applying Kirchhoff's law to a purely resistive circuit is simple because it gives an algebraic equation which is easier to solve. Now, when we apply the same law for RC and RL circuits, it produces a differential equation. So, it would be little bit difficult to solve when compared with the algebraic equation which we get when we solve the resistive circuit using Kirchhoff's law. Now, the differential equations resulting from analyzing the RC and RL circuits are of the first order. So, that is why we call these type of circuits as first order circuit. So, we can say that first order circuit is characterized by a first order differential equation. So, wherever you see that there is a first order differential equation coming, then we can say this is our first order circuit. Now, we have two ways to excite these first order circuits. The first way is that we will excite the circuit by using initial conditions of the storage elements in the circuit. So, that means that initially if you charge either capacitor or inductor and insert that charged capacitor and the inductor into the circuit, then the circuit will have only the source of energy as the total energy stored in either capacitor or inductor. So, there will not be any external voltage or current source to provide the energy. So, these type of circuits are called source free circuits because we do not have any external source available in that circuit. We have the capacitor and inductor available in the circuit which has some initial energy stored. So, we assume that energy is initially stored in those elements and this energy will cause current to flow in the circuit and gradually it will dissipate in the resistors, because when we talk about RC or RL circuit, we have either whether we have capacitor or inductor, we will have resistor either in series or parallel in the circuit. So, that means that the resistive component would be responsible to gradually dissipating the energy which was previously stored in the capacitor or inductor. So, it is although source free circuit, that means that it is free of independent sources, but there may be some dependent sources. So, we will see those cases when we progress in this particular lecture. So, the second way is that you excite the first order circuit by independent source. So, we have the first case where you do not have any source, so called as a source free circuit. Here the second is you excite the first order circuit by applying an independent source. So, now first let us try to understand what do you mean by source free RC circuit. Source free RC circuit means we do not have any external voltage or current source connected to the circuit. So, that is why it is source free. So, how we can realize it? The source free RC circuit will occur when a DC source is suddenly disconnected. So, suppose if you have a voltage source here connected through some switch. So, you have a voltage source here, that may be some voltage V. What we have done? We have initially connected the switch, and then after some time suddenly we have disconnected this particular switch. So, what will happen in that case? When we apply voltage across capacitor, capacitor will get charged and the energy would be stored, and when we disconnect, the circuit would be like this as shown in the figure. So, now let us consider the series combination of resistor and it is initially charged, means energy is stored in the capacitor. So, we will see that how the energy stored in the capacitor will be released through the resistor which is there in the circuit. So, now you will see that the figure which is shown in this slide, the resistor and capacitor we are seeing here as a single one, but it can be equivalent resistance or equivalent capacitance of the combination of resistors and capacitors. So, if you have multiple capacitors, multiple resistors in the circuit, you can club all of them and create an equivalent RC circuit. So, where C and R can be considered as an equivalent capacitor and equivalent resistance. Now, what we have to do? We have to find out the circuit response. Circuit response means the manner in which the circuit will react when the energy stored in the element, which is capacitor in this case, is released. So, let us see how the performance of the circuit would be when you have the capacitor initially charged and connected to the resistor in parallel. So, what will happen in this case? Since capacitor is initially charged, so we can assume that suppose at time t is equal to 0, the capacitor was having some initial voltage, say V naught. So, this initial voltage you will see which is there across the capacitor at time t is equal to 0, right. So, the value of energy which would be stored in the capacitor would be half of C V naught square. Now, we know that when we see this particular circuit, there would be one loop, and if you apply Kirchhoff current law at this particular node, what you will get? You will get simply IC plus IR equal to 0. So, you can write using KCL IC plus IR is equal to 0. Now, what is IC? As you know that current which is flowing through the capacitor is nothing but C multiplied by dV by dt. Voltage is time dependent. So, IC is C dV by dt, and resistor R is nothing but any voltage V across the resistor divided by the value of resistor. So, at any time t, we can say the voltage across the resistor or voltage across the capacitors, because these two are in parallel. So, voltage will remain same across both of the elements. The value of voltage is say V. So, what we have to do? We have to put the values of IC and IR in the equation. We will get C dV by dt plus V by R equal to 0. Now, this is our first order differential equation. So, why will say is first order differential equation? Because only first derivative of voltage V is involved. So, now what we have to do? We have to rearrange the terms. So, when we rearrange, we can simply write dV upon V is equal to minus RC minus 1 by RC dt. So, this is the equation. If you rearrange, you can simply write them as dV by V is equal to minus 1 by RC dt. Now, next task what we have to do is integrate at both sides. So, when we integrate with respect to t at this side and with respect to v at this side, what we will get? This will be the integration of this would be ln v minus 1 by RC is anyway the constant component. So, it will become minus t by RC after integration plus some constant term. So, in this case, for simplicity we will assume that the constant term is ln A, where A is the integration constant. So, what we can write? We can simply write the above equation as ln V. When you keep the ln components together, it will become ln V by A is equal to minus T by RC. So, next task what we have to do? We have to take powers of E on both sides, that is exponent. So, if you take power of E on both sides, so e to the power ln V by A will become simply V by A, and you will get this component as equal to minus T by RC. So, you can simply write V is equal to A into e to the power minus T by RC. Now, we assume that as per initial condition, when V is equal to 0 is voltage V naught. So, that means the value of A will be V naught. So, we put the value of A here and we get the voltage V as V naught e to the power minus T by RC. So, here you will see that the voltage across both of the components V, whether it is capacitor or resistor, is a time varying component. So, this shows that the voltage response of RC circuit is exponential decay of initial voltage. Now, since the response is due to the initial energy stored and physical characteristic of the circuit, so this will not be due to any other external voltage or current source. This is simply termed as natural response of the circuit. So, when we say that there is no external source connected to the circuit and the internal energy is dissipated, the response of the circuit is called natural response of the circuit. So, we can simply say that natural response of the circuit refers to the behavior that will be in terms of voltage and current of the circuit itself with no external sources of excitation. Now, how you will represent it graphically? When you represent the natural response graphically, it will be like as shown in the figure below. So, here you will see when you have the component V t is equal to V naught e to the power minus T by RC. So, let us assume that there is another component called time constant and it is denoted by lowercase Greek letter, which we generally say as tau. So, let us say that this time constant tau is nothing but the value of R into C. So, if you put the value of tau in the circuit, the voltage V will become V naught into e to the power minus t by tau. So, when you plot the this particular function with respect to time, what you will see that it is exponentially decaying. So, when you see it is decaying, when we take the time t is equal to 0, we know that the initial value of voltage was V naught, and then after that, because of this factor, it is decaying, and eventually the all energy would be dissipated in the resistor. So, when we say t is equal to 0, we say it is a initial condition. So, the natural response depends on the nature of the circuit alone with no external sources. In fact, circuit has a response only because of the energy initially stored in the capacitor. So, the natural response will have only the internal energy to be dissipated in the circuit. Now, one important thing which we have to know that when time t is equal to tau, that means if you replace t with tau, this would simply become e to the power minus 1. So, at that particular point of time, the value of V naught would be minus 0.368 V naught. Now, what does it mean? Let us see. So, when we say that the time t is equal to time constant tau, the response will decay by a factor of 1 by e, that is e to the power minus 1. It means that it will decay by 36.8% of its initial value. So, when we simplify by replacing R c as t is equal to tau, we get this value. So, we say that when we represent tau in the circuit, V naught V t will become V naught into e to the power minus t by tau. So, if you plot the value of V t by V naught, so that is if you take V naught by in denominator, so this will become V t by V naught is equal to e to the power minus t by tau. So, what we will do? We will plot this value with respect to time t, and let us take time t as a multiple of tau, that is the time constant. So, if you compare, you will come to know that after 5 tau, that means after 5 time constants, the value of voltage V t is less than 1%. So, what we can say that the capacitor is fully discharged, or alternatively you can say it is fully charged after 5 time constants. So, means it takes 5 tau for the circuit to reach its final state or steady state when no changes take place with time. So, every time interval of tau, the voltage is reduced by 36.8% of its previous value. So, this you can see from this particular table also, that every increment of time equal to tau, the value of the voltage would reduce by 36.8% of its previous value. Why? Because when you say V t plus tau, that means that it is simply V t by E. So, if you keep on changing the value of t, this will always be equal to 36.8% of V t. So, this would be regardless of any value of t. So, if you put the value of t as tau, 2 tau or 3 tau, you will see that whatever the value you get is 36.8% of its previous value. Now, smaller the time constant, more rapidly the voltage will decrease. So, that means that you have faster time response of the RC circuit. So, if you see this particular figure, when time constant is small, that tau, that is nothing but R C, the product of R and C. If it is small, the slope of the curve shows that the voltage is decaying very fast as compared to others. So, more you decrease the value of tau, more speedily would be the decay of voltage in the circuit, and we have tau larger, then you will see slow response of the circuit. So, we can say that a small time constant will give us a fast response and it will reach the steady state quickly, whereas when we have large time constant, it will give slow response because it takes longer time to reach to its steady state value. Now, at any rate, whether it is time constant small or large, circuit will reach at its steady state in 5 time constant, because in 5 time constants the circuit if voltage is there, then voltage value will decrease to less than 1% of its initial value. So, the value of time constant is small or large will not impact the steady state time, it will always be 5 times of the time constant. So, from time perspective, when time constant is large, the more time the system will take to reach its steady state value. When time constant is small, means 5 into time constant would be small in that case, and the circuit will reach to steady state value quickly. Now, using voltage V t, we can find the current. How will find the current? You can simply write current I, which is flowing across the resistance R, is nothing but the voltage across resistor, that was V naught into e to the power minus t by tau divided by the resistor R. Now, if power dissipated in the resistor is P at particular time t, then the instantaneous power would be V into I R, and this would be V naught square by R e to the power minus 2 t by tau. So, for V we will have V naught into e to the power minus t by tau. For I R again we will have V naught by R e to the power minus t by tau. So, we will have two components of e to the power minus t by tau, that is why it has become e to the power minus 2 times of t by tau. Now, the energy absorbed by the resistor up to a particular time, say t, can be given as the integral of p dt between 0 to t. So, if you integrate this, what you will get? You will get 1 by 2 c V naught square 1 minus e to the power minus t by tau. So, how you got c? Because you will have tau component coming here, and r will, you can replace tau as c into r, then r and the r in the numerator will be cancelled out. So, you will finally get half c V naught square into 1 minus e to the power minus 2 t by tau. Now, if you see this equation, at time t is equal to 0, this factor will be 0. So, what will happen in that case? You will get the value of this component as half c V naught square. So, when you say that at time t is equal to infinity, this term will become 0. So, this will become half c V naught square. So, you say that when time reaches, when time goes to infinity, the energy stored, energy dissipated in the resistor would be half c V naught square. So, that energy is nothing but the initial energy which was stored in the capacitor. So, we will say that the total energy which was there in the capacitor is discharged in the resistor in time that is infinity. So, it will take infinitely longer time to finally dissipate energy completely from which is available in the capacitor. Now, there are two important points to remember when we work on the source free RC circuit. One is that find the initial voltage V naught. So, that means at time t is equal to 0, what would be the value of initial voltage across the capacitor, and then find the value of time constant tau. When we get these two values, we can simply use the equation which we derived, that is for IR it is V naught by R e to the power minus t by tau, and find the various parameters like voltage or current in the circuit. So, the time constant is the same regardless of what output is defined to be. So, in finding the time constant tau, that is equal to RC, R is often the Thevenin equivalent resistance. So, when you have given the larger circuit and you want to find out the circuit response, you can simply use the Thevenin theorem, and R would be simply a Thevenin equivalent resistance at the terminal of capacitor. So, that means that if you take out the capacitor and find the value of Thevenin resistance, that would be sufficient to find the time response of the circuit. So, let us now understand the concept with the help of one example, so that you can understand the concept clearly. If you see this particular figure, in this figure let the initial voltage across capacitor is 15 volt. So, what we have to do? We have to find the value of Vc, Vx and Ix for time t greater than 0. So, any time t greater than 0, we have to find out the value of Vc, Vx and Ix in terms of time t. So, what you will do? First you will find the equivalent resistance, or you can say the Thevenin resistance at the capacitor terminal, and then we will obtain the capacitor voltage Vc, and then from Vc we will determine the value of Vx and Ix. Now, 8 ohm and 12 ohm resistors are in series, and this combination is in parallel with 5 ohm resistance. So, if you see these two terminals and find out the Thevenin equivalent resistance across these two terminals, you will simply see that the series combination of these two is in parallel with 5 ohm resistance. So, equivalent resistance, or you can say Thevenin resistance, would be 20, that is the total value of series resistance, 12 into 8, 12 plus 8, that is 20, into 5 divided by 20 plus 5. So, you get finally the Thevenin equivalent resistance, or you can say R equivalent, is 4 ohm. So, now finally the R equivalent, that is 4 ohm, is connected in parallel with 0.1 farad capacitor, who is having initial voltage as 15 volt. So, first what you have to do? We have been given the initial condition. Next we have to find out the value of time constant. So, time constant is nothing but the equivalent resistance R into C. So, you get time constant as 0.4 second. So, next what we have to do? We can just simply put the value of tau and initial voltage V naught in the equation, and we get the value of voltage across the capacitor at any time t is nothing but 15 into e to the power minus 2.5 t. Now, you can use voltage division to get the voltage Vx. What is voltage Vx? That is voltage across 12 ohm resistance. So, when you use the voltage division, you will simply get Vx is nothing but 12 divided by 12 plus 8, 12 plus 8 are in series. So, voltage across these will be 12 divided by 12 plus 8 into V. So, you simply get V x is 9 into e to the power minus 2.5 t volt. So, finally, you can find the value of current flowing through the resistance, that is 12 ohm resistance here, that would be V x by 12, and you will get value of current I x as 0.75 e to the power minus 2.5 t ampere. So, with this we close our today's session. In this session we discuss about the natural response of RC circuit, and in next session we will discuss about the natural response of RL circuit. Thank you.